Hey folks, welcome back again to Advent of Code in F#. I'm running a bit late, as in today we're the 29th of December. I'm still solving day 10. But yeah, I had a busy end of year, but I'm still having fun solving these puzzles, so I'm just running a bit behind. That is all. Today I won't be live solving part 10, because I actually solved it already, as you can see. And it was a tricky one for part 2, at least for me. But I found out about a cool new algorithm and I wanted to share this with you, so here we are. So I'm gonna go into explaining mode or summarizing mode and not live coding mode today for day 10. So day 10, to freshen up or to jog up your memory, is the one with the pipes, the horizontal, vertical pipes and the bends. Part 1 asks us to find the loop or the cycle in our input. And part 2 asks us to find how many locations are inside the loop. So we need to count every spot that is inside the cycle we found in part 1. And it was very tricky, and it was not very tricky, but it was pretty tricky. And I was playing around with a flood fill algorithm, like where you drop a bucket of paint and you see where the paint spreads. And that would work, except that maybe you have to do it twice because you don't know which way is in or out initially. And I think that would work, but I found out about another approach called raycasting, and that approach is so cool that I wanted to share it with you. So let's do a quick googly woogly. Here we go. So it's called point in polygon or raycasting algorithm, and this image explains it quite nicely, or the abstract idea of the algorithm at least. And it's you take a point you want to take a look at, and then you just cast a ray from that point to somewhere else, like say to the right, infinitely to the right. And you count the number of intersections with the polygon, or in our example with the loop. And if it's even, like 0, 2, or 4, we are outside because we crossed we intersected with the polygon an even number of times. If we are inside the polygon and we cast a ray infinitely outward, for example here, we cross 1, 2, 3 times. So we cross an uneven amount of times with our cycle. So that's by definition, we jumped out, we jumped in again, and we jumped out again, and then we never saw the polygon again. So that means we are in. And that's the idea of a raycasting algorithm. But it was a bit trickier for our example because we didn't have like clean linear equations or a clean polygon. We had these pipes with weird bends. So it took a lot of trying out and drawing out in my notebook. But I came up with a solution, and let's see if I can draw it out as well to kind of make sense. Because there's a lot of solutions out on YouTube that just like plainly say, okay, this is what you should be doing, without actually explaining. So I want to go a bit into explaining mode, how we get where we are for the raycasting algorithm. So we are doing raycasting. We have some assumptions here. First assumption is we are casting our rays. So let's quickly draw our cycle. It's not my cycle, but it's a cycle. Some assumptions. So we have a point somewhere. It could be in the cycle, could be out the cycle, anywhere. And let's assume that we are casting our rays to the right. So all our rays go this way. Now this already tells us something. This tells us that crosses don't happen if we see horizontal pipes. So if we see this character on our ray, that means we don't know anything. We are right on the edge of something, so we can't count that as an intersection. It also tells us that the vertical pipe, is very much across, so that's an intersection. If we encounter this on one of our rays that we cast, we are crossing in or out of the polygon. And then the other ones are the interesting ones. Those are the bends. You have a couple of configurations here. I think I'm kind of summing them up right here. Yeah, and these are the only ones actually I need to take a look at, because all the other ones that start, like say, that start with an open connection on the left, those I will never encounter because I only count those green dots I take a look at all the points in my grid that are not part of the loop. So I never end up with a pixel here that could potentially see this bend. No, I only start like from here, and this will always have a bend that is not connected to the left. So all the ones with an opening to the left, I don't have to take a look at. So these are all the ones with an opening to the right. And then there's yet another edge case, and this is the tricky part. If we meet a bend like this, say, what's that? I don't know what the character was anymore, but if you meet a bend like this, if we are here, this is my pixel, and I cast a ray, and I meet like these two things, and kind of just skirting the edge of my loop. I'm not like crossing it, so this is not an intersection. Same thing with the one above. We're just skirting the outset, we're not actually intersecting with it. So this is not an intersection either. So the only two relevant bendy parts are these ones, where we kind of make a vertical snake line that we intersect. So what do we do for part 2? We do raycasting, and we disregard horizontal lines. We count vertical lines as definite intersection. And once we meet these bendy bends, we only count the ones if they have a vertical snake. So there's only these two are the only bendy parts that count as an intersection. So let's take a look at the code quickly. I have not made a video, I think, for part 1. So I'm going to go over part 1 as well, and then we're going to see how this raycasting algorithm works in F# code. So I am using, for part 1 and for part 2 as well, but I'm using an array2D, which is a 2D matrix, and it has some benefits with regards to actual lists of lists, or with hash maps or lookup maps. It's faster than hash maps. It's like a O1 indexing, so it's really fast to look up stuff, and that's great for today because we need to look at the neighbors at certain locations. And it's better than a list of a list. It's not really relevant for today. Yeah, maybe it is. It has really nice slicing support. I don't think I use it for today or for day 10, but if you say I only want a submatrix of this 2D matrix, and I want the second until the 4th row and the 3rd until the 5th column, or the entire column for every row from 2 to 4, all that kind of crazy slicing in 2D matrices, this is where array2D really shines. But I don't think we actually use it in day 10, so let's hold that thought for another advent of code. But anyway, we use it for our representation of the grid. I have some aliases here, so our pipes are just characters, but a bit more explicitly typed. I don't really parse them into union type. I just keep the characters around because they are very visual. If I transform this to some kind of textual representation, we would lose a lot of the visual clearness. This is something we've seen before as well. I like to have a module and a type of the same name, so that I can like put functions that belong to this type or that work on this type closer to the actual place where you would look for them. And I just have some aliases like finding an index of an element in the grid to figure out the starting position. That's something we do here. So it's literally looping over all the things, and if we hit the match, if we hit the matching element, we return the x and y coordinate, or the row and column. And I have one that just indexes, or that just finds the element at a certain row and column. So it's just an accessor. And our parse today is really simple. I just push in the 2D list of lists of characters into an array2D, and ta-da, we have our matrix. I do have a union type for my directions, and I have a sequence computation expression. I think we've already used that this year. So it's just something that generates a sequence, and we do conditional yields here. So we yield elements of the sequence only if we are in bounds. If we are out of bounds, we don't yield the right neighbor, for example, if we are at the right edge. So this is a cool way to generate all neighboring locations, or all neighbors and their locations, with the if inside a sequence computation expression. Then we have some helper functions to flip directions. That's easy. If you have a starting location and you want to see what's above me and does it connect with me, you kind of have to flip the directions. So we have a helper like that. And then we have another helper function that says like, okay, given a pipe, does it have an opening or does it have a connection in a certain direction? That's just an exhaustive list of everything. And some delta calculations, like if I want to go east and I'm here, what's the location to the east of me? So that's a bit of offsets. And then we have the build cycle. That's for part 1, where we actually do a search for the cycle. And it's a pretty easy search. We have a starting location. We can figure out like what piece is this, where are my neighbors that connect to me, and then you can just start taking one step and figuring out all the connecting directions and figuring out neighbors that have open connections on the flipped side. So it's pretty basic, or it's a pretty self-explanatory search algorithm if you play around with the problem for a while. As always, I use states and I use, I think, some recursion. Yes, we do. So we just use some recursion. And the state we are keeping track of is, let's maybe take another look at that if my compiler will help me. There we go. So we keep track of where we are right now in the search and where we are facing. Are we facing east-west? So we're basically a little robot running over the cycle. It's very much like the Mars rover Kata, if that rings a bell. And we keep track of every node we are traversed on our path to build up the loop or the cycle. Because we're using characters and not union types, we don't have exhaustive pattern matching, so you see a lot of, oh, this should never happen kind of errors, but for Advent of Code, that's more than enough, so I kept it in. So yeah, this is the part 1, figure out cycle. And with all those helper functions, it's really easy. It's like, okay, I am right here in this location. I am facing this direction. Well, what's the XY coordinate of that place? Okay, cool. And then we look up, okay, what piece is in there? And then we just, this is the halting condition. If we are back at where we started initially, we're done. And we just return the loop or the cycle. Otherwise, we figure out, okay, if I step onto that next pipe, what's my next facing direction, because that pipe will kind of bend me and swirl me around. And we build the cycle and we just continue. So it's a pretty straightforward search algorithm or recursive cycle build algorithm. These are also some helpers to figure out which piece the actual starting piece is, because it's S, but S is one of those tricky ones. I just noticed that I'm not even... I think my code works for the examples and my input, but for any other inputs, it might crash with a to-do. That's how life works during Advent of Code, I guess. But you could exhaustively pattern match on all the possible pipe types, but I'm not, evidently not doing that. And this is then the main loop that uses that build cycle function we just saw. We parse, that's the array to D thing. We find our S. We find the neighbors of the starting location, and that's just things that are next to the S that have a connection in the opposite sides of where we're looking. So if I'm looking to my eastern neighbor, it has to have a connection or an opening on its west side, and that's what you're seeing here. If we know the neighbors that connect to me as a starting location, we can figure out the starting pipe or the starting piece. So that's what you're seeing here. And then we just can call our hey, figure out the cycle or figure out the loop for me, recursive function, and we're done for part 1. Part 2 was the raycasting, and that's the thing that got me excited about today's puzzle. And we discussed the problem right here, so we only have 1, 2, 3 cases to take into account as intersections, and if we count the number of intersections, if it's even, we're out, if it's odd, we're in. That's what we're gonna see here. So this is the in or out type for our raycast algorithm, and this is the raycast algorithm itself. It takes the cycle. We kind of sort it because we are casting our rays to the right. So in the example, we are always casting our rays to the right. So our cycle has to be sorted. So we take a look at every element of the cycle from left to right. That's why we're sorting in here. And then we just find all the pipes that are to the right of the location. So we take the cycle and location, we figure out everything on the right. And as I said, horizontal pipes, we don't care if we're casting rays to the right. We're just overlapping with the cycle. We're not really intersecting it. And then we split our remaining pipes of the cycle by verticals and bends. This other case is all the bends. These others are like all the bends. And every vertical is just a definite intersection, so that counts as a collision or an intersection with the cycle. And the bends, they don't always count as intersections. That's what I was drawing. So how I do that is I take all the non-vertical pipes that are not horizontal, so all the bendy pieces, I just smoosh them together in chunks by size 2. That's a function I don't use a lot, so let's take a look at that. If you do chunk by size 2 on a list, for example 1 to 4, this gives you something, I hope. Yeah, there we go. So it chunks the input list into sublists of exactly a size you provide. So I just take every pair of bends and then I take a look at, is this one of the vertical snaky wakey bits? So these are all the cases we discussed on the drawing, and there's only 2 of them that are actually relevant and actually count as a collision or an intersection. Once we know the number of definite verticals and bendy bend intersections, we know the total number of intersections with our polygon or cycle. And if it's even, we're out. If it's odd, we're in. That's the definition of the raycasting algorithm. So that's actually how I solved part 2. Really fun. Yeah, I had a lot of fun. Taking a look at this solve function. There's a lot of boilerplatey stuff going on. We found our loop. That's part 1. I generate all coordinates, and then I find all coordinates that are not part of the cycle. I sort my cycle, so I visit every part of the loop in order for my raycast algorithm. And then I just raycast for every point not in the loop to figure out whether it's in or out. And we count the number of ins. Easy as that. Left today. It took me a couple of hours to figure this out, and I needed a hint for that whole raycasting thing. But yeah, really pleasing puzzle. I had a lot of fun. It's not the slowest of solutions, so I'm really happy. Yeah, really happy with day 10, is it? Yeah. So this was Advent of Code in F#. No live coding today, but I promise we'll do more live coding in the coming days. See you next time. Bye-bye.